Hey guys, today we will continue in our series where we go through the courses in FPGA Academy. This is a design we will try to implement today. This design is part of Lab 3, Latches, Flip-Flops and Registers, and it's the last part, part 5. This is the description for the project, but before we read it, if you haven't seen the previous parts, you can watch them on my YouTube channel. Last time we implemented master-slave DFF, and we will use some of the code that we have implemented in the previous parts today. So I encourage you to watch it, and let's read the description for today's project. We wish to display the hexadecimal value of an 8-bit number A on the two 7-segment displays, hex 3, 2. We also wish to display the hex value of an 8-bit number B on the two 7-segment displays, hex 1 and 0. So we will have two numbers, A and B, as inputs, and we will display them on hex 7-segment displays. The values of A and B are inputs to the circuit which are provided by means of switches 7 to 0. So these inputs will be selected using switches. To input the values of A and B, first set the switches to the desired value of A, store the switches values in a register, and then change the switches to the desired value of B. So we will save A and B in register. So first we will set the switches, save A, then change the switches to another value and save it to B. Finally, use an adder to generate the arithmetic sum S equals A plus B. So we will add these two numbers and we will show the result on hex 5 and 4. And the carry out will be shown on LEDR 0. I will slightly change this description because I'm not sure how this is supposed to be implemented. 8-bit number shown on hex 3 and 2, so on two 7-segment displays, you can't really show 8-bit number because the highest number for 8-bit number is 255, so that's 3 digits, and you can't show 3 digits on two 7-segment displays. So I will be using 6-bit number, which is convenient because in the previous part we have implemented 6-bit binary number to BCD converter, so it will be easier to convert the 6-bit number, and also we will be able to show it on the 7-segment displays. So that's one of the changes. Let's look at the diagram here. We will use key 0 as reset for our registers. You can read it here. Write VHDL file that provides the necessary functionality. Use key 0 as an active low asynchronous reset and use key 1 as a clock input. So key 0 will be reset and it will be active low because the keys in DE10 standard or DE1 SOC in the board that I will be using, they are active when they are not pressed, they are actually showing 1, and when they are pressed, they are actually driven to 0. So they will be active low, which means that it will be activated when it's pressed, when it's 0, and it's asynchronous, which means it's not driven by clock. So we will have key 0 and key 1 as clock and reset. And then I will use switch 0 as select, and we will select with this switch if we want to save it to register, if we want to save number A or number B. And then also we will have switches 6 to 1 as our inputs. If switch will be 0, we will select A, and if switch 0 will be 1, then we select or we save B. So if it's 0, we will save A to register. If it's 1, then we will save B to register. We will implement something like this. We will use master-slave DFFs, and we will create in total 6 of them for A and 6 of them for B to save the number. And then when we have them saved, we will show them on hexadecimal 7-segment displays, A and B. And then we will add them here. We will convert the sum to BCD So we will get two outputs that will be 4-bit BCD numbers. And then we will show the result on 7-segment displays as well. Also, the carryout of the addition will be shown on LEDR0. So that's all for the description. And now let's try to implement it. First, we will just try to show addition of two numbers that we will hard code to VHDL, and then we will add the registers for the numbers later. So first we will show the addition. Let's do it now. I have my quarters project here, part 5, and I have, I will set it as top level entity, and I have switches, keys as inputs, and LEDR and 6 hexadecimal 7-segment displays as output. Also, I have two components which we have implemented in the previous parts. One that will show the BCD number to hexadecimal 7-segment display, and one which will convert 6-bit binary number to BCD. We can look at the code. So 6-bit binary number to BCD, we have implemented this in previous part. We have implemented this in part 7, and the algorithm for this is called double double. So that's the name of the part. So you can watch it here if you are interested in how this works. And this is the code for the double double algorithm. So we'll use this, and then our code for BCD to 7-segment display. Also, we will use adder 4-bit, which we have implemented also in the last part. It's called 4-bit adder, part 5. And today we need 6-bit binary number adder, so we will change this code to 6-bit. That's the first thing we'll do. And it will take as inputs 6-bit binary numbers, and it will add them. So let's implement this. We will add two more full adders. That's a component that we have also created earlier. So 2, 3, 4, and 5. And we will also have to create 4 and 5. That's for our carry out. So 4 and 5. Here it will be 5, 4, 3, and this is gonna be 3, 4, and 5. And our carry out, let's just save it in the carry out. We don't need this. Well, let's create a new one more. That will be called carry out, and we will save the carry out there. So we have as input carry in, and then A and B, 6-bit binary. Then we have 6-bit binary output and carry out also as STD logic. We have our carry out here. 1, 2, 3, 4, 5. So this seems to be correct. We don't need this actually. And now we will import this to our entity as well. We will change code here, and now it seems all right. So first we will take two numbers. So let's say we have two signals, A, and it's going to be STD logic vector 5 down to 0 with initial value, and this initial value will be, let's say, 0, 0, 0, 0, 1. And let's create one more. And this one will be, so this is 1 and 2. And now we will show them on the hexadecimal 7-segment display. Let's import 2 instances, or we can actually import 3. We will use the last one later. So let's create 3 instances. So this will be instance 0, and it will be instance of this component, port map. And as input, we will input our binary number. So that's gonna be A. And we will create 2 more signals, BCD 0 and it's gonna be STD logic vector. And we can actually create array of these. So let's look at how to create array in VHDL. So we will copy this code and we will create type BCD array is array, and here it's gonna be let's create it like this. So it's gonna be 1 to 4 of STD logic vector 3 down to 0. And we will create, we need 1 to 6. And it will create, or you can do 0 to 5. And signal of this type. So now we can call it array. And here we will map it to BCD array 0, BCD array 1. We will create 1 more or 2 more instances. This is gonna be called instance 1 and instance 2. Here we have B. This is gonna be our sum. So we can call it sum, and sum will be signal STD logic vector. And it's gonna be also 5 down to 0. And this is gonna be 2, 3, 4, and 5. Then we will have our hex. We will create these instances. We also will need 3 instances of this port map, and here we will give it our 2 BCDs. So and this actually takes only 1 BCD, so we need 6 instances, and we'll give it BCDs like this. So Here we will input BCD array 0. It's gonna be on hex. This is our A, so that's 5 and 4. So this is gonna be 4. So 6 instances, 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. This will be 5. This will be B. So that's 2 and 3, and this is 0 and 1. So this will be our sum. This will be number B, and this will be number A. And let's create this sum. So we have our 6-bit adder. So let's create one instance of this. And port map. Adder 6-bit that takes carry in. Carry in will be just 0. Then A and B. A and B. And we get our sum. And also carry out. So carry out will be LEDR 0. And let's copy this after. So we add our numbers, we save it to sum, and then sum will be shown on these two BCD numbers, and then we display the numbers on the 7-segment displays. And what else do we need? We need to convert. No. We have our adder. I think this is all we actually need to do, right? Let's close this. So let's test this out. Part 5 is our top level entity. Let's try to compile. Part 5. Hex is used but not declared. Oh, here it's not hex 4 but hex 4 like this. There are no parentheses. So let's delete those. Like this. And we need one more number here. Okay. And here we import some component that is not that we haven't imported here. So I will import it now. So our full adder entity needed this component. So I have imported it, and now the compilation is done. So we can test it on our board. So we will open the programmer and program the board. And you can see that we have 1, 2, and the sum is 3. So this is the correct outcome. So this seems to work, and we can continue. You can see it, and we can continue. And now we will try to implement the master-slave DFFs. So what we will do is we have to first create dlatch and also DFFs with reset. So we will create new file, vhdl, and we will copy our code from dlatch to this file, and we will call it dlatch reset n. and it will have one more input, reset n. And here we will say if reset n, and this is active low, which means that if it's not, or we can just say reset n equals 0, then and else if. Here q will be 0. Reset it. Let's save it. Let's save it in part 5. The latch reset n. So if the reset is 0, then we reset our output. Okay. So we have done the latch. Now we have to our positive master slave DFF. We also have to add our reset. So let's create one more VHDL file, and we will copy this again. I'll close these, and here we will say reset n. It will also have one more input, reset n, and here reset n, like this. And here we just have to input into our dlatch here reset n, and here as well reset n, and save it. We call this DFF reset n. Okay, we have created these in the previous part. So if you don't know what this code does, you can watch the previous parts. And we have them here. And now we will create our register to save the numbers. And we can probably create a new entity for this. So let's create a new entity, VHDL, and this entity, let's open 4. It will be very similar to this, so I will copy this and we will use this. This is gonna be called 6-bit register, maybe, or register 6-bit. It will have clock and not D, but reset N as well as inputs. And it will have, let's call it number as input. It will be std logic vector 5 down to 0. And then as output, it will give us also number. So let's call it Q. Let's call it Q. And it's gonna be, we can actually call this D as well. It's gonna be std logic. Let's save it as register 6-bit. And we want to import our only one, positive reset N. Here we have to add reset N. So let's call it DFF instance 0. And it's gonna be of this type. Here it will be D0 clock, then reset, and then output will be Q0. We have to copy this 5 more times. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And this should be enough. Register 6-bit, input, output. Okay. This seems to be correct. So let's import this entity into our part 5 here. And we will create 2 instances of this register here, or in the beginning. Register instance 0, port map, and this will take, how do we do this? So let's create a in and then a, no, let's, how do we do this? Let's call it a register. So that will be the output of the register, and then we have a in, but we don't actually need a in. This will be the initial value. Let's save it. Let's keep it. And here I will do with switch 0 select, and yeah, we actually need 2 more signals. So these don't need initial values, and they will be called A in and B in. Select A in, and it will be A in will be switch, and we set switch 6 to 1, 6 down to 1 when this is 0, or A in will be a register when it's 1. So what this will do, our switch 0 is our select. So here it will be, I will finish this code and then I will explain what this will do. This will be B and B like this. Yes. So if switch 0 is set to 0, then this A in will be a new value. And if it's not 0, then it will get the value from a register. And a register will be output of the registers. So basically, it will just output the Q and put it back as a D. So the value will not change. And for B, it's the inverse. So when switch is 1, we will get new values from switches. and when it's 0, then we will just get the old value from B register. And then here we will port map, and so this needs clock and reset. So clock, reset will be key, let's see which, key 0. And clock will be key 1. And now we have input, and input will be A in, and output will be A register. We create one more. Whoops, what happened? Create one more. Instance 1. And here it will be B and B. So now we should have in registers saved our A and B. And here, instead of A, we will say A register and B register. Since we are using positive, we are using positive edge, where is it? Here. Positive DFF. That means it will change on the rising edge of the clock. So when key 1 will be pressed, then it will change the value. And let's try to compile this. So we will select the inputs. Okay, we have some. Oh, here I don't need this. I don't actually. I have it here, right? So let's try to compile. And so we select the inputs here, then we save them in our registers. We add them. Key is used but not declared. Again, here we don't need the parentheses. Then we save. Then we add them. And here dlatch, it has to be dlatch reset n. We get the inputs, we save them in registers, we add them, then we show everything on the hexadecimal 7-segment displays. And here 1, 2, 3, 4, 5. Okay, hopefully no more errors, but there's probably gonna be more. No? Okay, nice. So then we show all the numbers, and here we actually, or we convert them to BCD, and here we actually show all of them. So that could be all for this part. Let's see if it works. Download the circuit onto your DE series board and test its functionality by toggling the switches and observing the output displays. Let's see. After compilation was done, I have found out that I have actually made a mistake. Key is std logic vector and not, it's not a one standalone value. So I have made it as a vector. So I have changed it here to be a vector, and I also will show the output of the key on LEDRs. And also I found one more, and that was in the process. I didn't add the reset to the sensitivity list, so it would not change the value when reset was pressed. And now I have compiled, so we can look at the result. I'll program my board, and now we can see that the values of the registers are not set, so they were set to all ones, so that means 63. And if I press reset now, they will all change to 0, so they will reset, and we can start setting up our numbers. So I will input maybe that this is 5. And when I press clock, we can see 5 changes for A. Now we will set B. I will do 6. I will press clock, and 6 was added, and now we can see 11 as the output. So it works correctly. I can press reset, and it's reset it. I will try to input, I don't know, let's say this number for B, and let's put, I don't know, this number for A, and we have 17 plus 7, and that's 44. So it's correct, and we have successfully implemented part 5 using this code. And next time we will look at lab 4 counters. We can open and look at it now. So we will use counter, or we will implement counters, and yeah, it's gonna be interesting. So if you wanna see next part, don't forget to subscribe, and I will see you in the next one. Bye.